Good day, grade 9 students, and we are about to proceed with tool number 5 in our series. And the series is trying to solve the problem for up in terms of if the animators use the correct number of balloons to lift a house as they did in up. So this tool may or may not be useful when solving the problem with up, but again, you'll see how important it is for manufacturing and packaging. What we're dealing with today is called surface area. And we're going to start with a problem. And hopefully by the end of today's activity, you should be able to solve this problem. Pepsi-Cola is designing a new can to hold its product. The volume of the can must be 355 milliliters. And it's looking at two designs. And it's your job to determine which design of can is better. So here's can A, and here is can B. Now, in class, we talked about what makes a good can. And some of you were saying, the ergonomics, how the look and the feel of the can is important. How much it can hold. The material it's made from. But by the end of this discussion, we quickly realized that one of the main features of an effective or of a good can is the amount of material needed to create one, the surface area. And we realized that if a company manufactures cans or products, if they're able to save on the surface area or save on the packaging without compromising the amount of material they are trying to ship out, in this case 255 is the volume, then that would save the company money in the long run for packaging because they are using less material to create the can. So hopefully by the end of today's activity, you'll be able to solve the can problem, which is a better design, can A or can B. And again, we could look at look, feel, volume, material, but we're going to ultimately make our decision based on surface area. And just to recap, 1 milliliter is the same as 1 centimeter cubed. So it's the same. Now think about this. If something's 1 centimeter cubed, so I'm just going to approximate the size of 1 centimeter cubed just to show you. If a company is able to save even 1 centimeter cube, so that's probably 1 centimeter square. So this is 1 by 1. If we're able if a company is able to save that in terms of packaging every single day, and for instance, if Pepsi-Cola were to produce 5 million cans each day, and they're saving one centimeter square of aluminum each day, well, think about the money that company can save when designing a can. So we're going to look at the surface, what surface area is for a definition. Again, you'll have this in your notes, but the surface area represents the amount of flat space that forms the shape of that forms the surface of a shape. And if you want to roll the can, what shape will you have? So in terms of the can, we're going to look at the surface area of a cylinder. If I were to cut a can open, how would this shape look like? So how would the flat shape can look like? So we're going to do this with a two-dimensional smartboard, but now we're going to take this can and I'm going to pull this tab. As I pull it, you're going to see the different parts that make up the can. So this represents, as I'm pulling, this section here represents the side of the can. And you can see we have the top and we have the bottom of the can, which are the circle. And notice I emphasize on this red part. This is important in terms of finding the surface area. This red line that I'm going to highlight here also represents this highlighted red line around the can. And if you remember your terminology for measurement, that represents the circumference of our circle, of the base or of the top. And this part of the can just represents the side of the can. And so it looks like it's a rectangle. So we see when we create this, finding the surface area of a cylinder, we're actually dealing with two-dimensional objects. We're dealing with two circles and a rectangle. So now we're going to try to come up with the formula to solve the surface area. So just to recap, on the can, on the three-dimensional can, here's the radius, and when we unfold it or unroll it, we see the radius still part of the circle. Take a look at the height. This represents the height of the can. When we roll it, this represents the height of the rectangle. And as I showed you earlier, here's the circumference of the circle, but when we unroll it, it becomes a straight line. The circumference now becomes the length of the rectangle. And as you recall in class, the circumference of a circle is equal to 2 pi r, and that's why we have the formula written below, 2 pi r. So now all these conditions, or all these parts of the can, we're going to put them together to come up with, the surface area of an entire Pepsi Cola can. As you can see, we have three shapes, two of the same shapes and one rectangle, two circles and a rectangle. All right, so let's try to recap. How do we calculate the area of this circle? Well, as you saw from class, or as we saw, the area of a circle is pi r squared. How do we calculate the area of a rectangle? We know that the area of the rectangle is length times width. But what does this represent? 2 pi r. And what does h represent? Just to recap, here is the h, which represents the width of the rectangle. The length represents the circumference of the circle, which is 2 pi r, and that's how we're getting these values. So here's the length, and there's the width. And finally, we have another circle, which we calculate the area by the formula pi r squared. So let's try to put everything together. So basically, to find the surface area of this shape, we're adding a circle. Looks like a composite figure. Two circles plus a rectangle, or circle, rectangle, circle. We're going to add them all together, the areas of each of those shapes. So here's the surface area. So just to emphasize where these come from, that pi r squared represents the area of the first circle. This pi r squared represents the area of the second circle. And what does this represent? The middle part, 2 pi r times h, represents the area of the rectangle. So let's see what else we have when we start going through this problem. So we're going to simplify. Instead of writing pi r squared, we have two of them, and that's where this comes from. The 2 pi r squared represents the two circles. So we're going to combine them and add them together. They're like terms. So we're putting this and that together to form 2 pi r squared. And notice 2 pi r h still remains the same. Now you'll see this formula as well on your formula sheet. So this is one form of the formula, 2 pi r squared plus 2 pi r h. Later on in the course we're going to see, well, how do we get this form of the formula? And if I were to do something called expanding, if I multiply that in, I would get the same as the formula above. But these two are identical formulas. So I just want to make sure that you do see this formula in play. So you might see it one time on a sheet, and you should recognize that that's the surface area of a cylinder. So our first problem that is going to involve the surface area of a cylinder is a greenhouse problem. This is actually taken from an EQAO question a few years back. It says the figure below, or the figure shows a greenhouse roof in the shape of a half cylinder. What is the approximate surface area of the curved roof? Now notice that it's saying just the curved roof. So we're just going to calculate, or we're going to find the surface area just for this part right here, not the ends. We don't want to calculate the ends because all we want is a curved roof. So we'll write down the surface area formula. And then we're just going to, since I remember for a full cylinder, the surface area is 2 pi r squared for the two circles plus 2 pi r circumference times height. But in this case, the formula does not call for the use of the areas of the circles because we just want the curved part. But this represents for a full cylinder. So what we have to do, since it's just half of it, we have to divide our answer by 2. So let's write down what our true formula is in this case. We modified the surface area of a cylinder formula. And now we just do our substitutions. So we're going to substitute 2 times 3.14. Radius in this case is not 6. It's actually half of 6, which is 3. And the height of the cylinder is 30. We're going to divide everything by 2. So we can do this all in one shot using our calculator. So I'm going to get out the calculator. Okay, so let's start entering our values using the calculator. So I'm going to use the pi button, and I probably recommend that if you have a nice scientific calculator, it's more accurate to use a pi button than 3.14 times 3 times 30. So there's our numerator, and with that answer, I divide by 2, and I should get an answer that's present there. An answer I get 282.74. 282.7 meters, not centimeters, squared. So the best answer that follows this model is moving on to the next question. So now we're going to investigate how to find the surface area of a rectangular based prism. So it's the same thing. We're going to take a look at this shape and just notice the length, the width, and the height where they are as I pull it. So I'm going to pull this. So that represents our, as I'm pulling it, starts representing our view of the shape here. So just to show you, that's like our first width, you can say. Then comes our length. Then comes our width, and then comes our length again. And here's the height. This represents the top and the bottom. So what we just created is something, as you probably heard before, something called a net. So how do we calculate the surface area of this shape? Well, we know we can calculate the area of the top and the bottom. It's just the area of the base times 2, because there's 2 of the same bases since it's a prism. And in this case, it's a rectangle, so the area is length times width. And the same thing goes for the bottom. But now let's truly investigate what the other two variables are. So what the other two dimensions are. So we need to find the area of this entire rectangle. So here's our height, and that still represents the height of the prism. And now, if I just use different colors, just to emphasize, I'm going to toggle back and forth. If this represents the width, and there's the width, and this is the length, and here's the other length. Oops, and you can't really see it. I should use a different color pen. So let's use red here. There's the length, and here's the length. Then I'll use a green pen. Here's the other width. I should have used the same green. This is the other width here. And finally, we get the length, and here's the length here. So what does this whole side length represent? Take a look at that. That whole side length represents the perimeter of the top. How do we calculate perimeter? It's length plus width plus length plus width, or 2L plus 2W. So now we can actually calculate the area of this rectangle, which is the perimeter of the top or the bottom times its height. So now we can put these 3 formulas together and come up with something that could be useful for all prisms. So let's take a look. So on this page, it just shows a simplified version of what we've done. You're going to see the formula also presented as below. So I'm going to actually give you the formula that might be more useful than the one on the next page. So when I put all these areas together, let's do this. Surface area of a prism is equal to the area of the bases. And how many do we have? Times 2, because there's 2 of them, plus the perimeter of the base times the height. Or the more proper way is 2 times the area of base. Notice I'm using a subscript, plus perimeter times h. And this, if you can understand this formula, it's actually easier it's more versatile for all types of prisms. The next page is going to show you another form of the formula, which you'll probably see on various formula sheets or on your Kiro formula sheet. So what the formula is doing is it's actually looking at the shapes as individual rectangles. So here's to find the area of that, it's width times height. Then we go on to the next rectangle. To find the area of that, it's length times the height. Then we go back. Same thing here is width times height. Then we find the area of this rectangle is length times height. And now notice the top and the bottom are length times width. And here it is, length times width. We have 2 of them. So if I were to just use color codes, here's the top, here's the bottom. Here's one of the sides of the can, here's the other side of the can, and here's the other 2 sides. And now we can put things together. We have 2 length times widths, so those 2 we can add together as 2 length times width. The length times heights, we have 2 of them, and the width times heights, we have 2 of them. So this is one form of the formula you see, or you'll see it a factored form, which we'll see later on in the course. 2 is factored out of all 3 terms, and it's outside of the bracket. And just to speed up the process, so now you know where the surface area comes from. We are just going to give you the formula for different shapes. So this is now a triangular-based prism. So when we open up the net, take a look here, side A, side B, side C. So if I use, again, some color codes, here's A, this is A, and here's B, this also represents B, and C will use purple, and here's C, okay? So that also, we can use the first formula for prism that we saw earlier, which is the perimeter times height, times the 2 times the area of the base. That's one way of the formula. But in terms of this, you will also see it like this, just like we saw previous. A times B plus B times H plus C times H plus B times L. And I'm going to give you the other formula too, just for the sake of things. Surface area equals 2 times the area of the base. So in this case, we have 2 times base. The area of the base is a triangle, so it's base times height. And they use L to represent the height of the triangle, just so it doesn't confuse with the height of the prism. So the area of the triangle is base times height, which is L, divided by 2. And we have 2 of them. Plus the perimeter of the triangle times the height of the prism. Now we can simplify this. If you recall fractions, I multiply numerator with numerator, denominator with denominator, and you'll end up finding that the 2's actually divide each other out. So this formula actually simplifies to base times height of the triangle plus perimeter times height. So you can use either formulas to do your calculations. The one here is, I think, the one that you'll see on an EQAO sheet, on the formula sheet. So moving along, we're just going to show you the surface area of now a pyramid. We do the same thing. And we're just going to deal with a square-based pyramid. So how do we find the surface area? Well, we know we can calculate the area of the base. In this case, it's base times base, or just base squared equals the area. And all the triangles are the same. So it's base, which is side. I should say, yeah, it's base times the height of the triangle. In this case, they use S divided by 2. And how many do we have of those? We have 4. So that's why we have the formula 4 times the area of a triangle. So we have 1, 2, 3, 4 plus the area of the base. And here's a simplified version of what we showed above. So how do we get from here, or how do we get from our version to this? So let's do this. Surface area equals 4 times base times side length divided by 2 plus area of the square, which is base squared. So what happens here is that the 2 and the 4 divide each other out. So 2 goes into 4 2 times, and we're left with base times height of the triangle plus base squared. So this is how we get from the picture to the formula that you'll see. Moving ahead is we're just going to give you the formula for the slant. Formula for the cone. So if I were to open the cone, you will see that the cone, let me see if I can draw it, it'll definitely form a circle as a base. I should use a different tool for that. So it'll definitely create a circle for the base, but the tops, if I can draw it well, it's also, if you open up a cone, and you did this in class, it almost looks like a complete circle, like a Pac-Man type shape, that sort of cut. Oops. That's a pretty brutal Pac-Man, but I think you get the point there. I'm hoping you understand. And you basically roll this together. This is open space, and the circle goes underneath. So the formula for this, you can see that the area of a circle is present. It's right here. And where does pi rs come from? Well, pi r squared is an area of another circle. This shape almost looks like an entire circle. So let me try to draw it a little bit better here. So I'm just going to put a complete circle, so that's what I'll do. Oops. Okay, so this is how it looks like, and just imagine now, so that's going to be the bottom, and I'm going to cut a part of it out like a Pac-Man figure to the radius. And so this part over here is cut out. Okay, so that doesn't exist, you cut it, and then after you fold the paper, or you bend the paper so that it forms a cone, and then that bottom part goes underneath the cone. So you can see it's almost two circles, and that's why the first part of the formula is pi r. Instead of using r squared, we use r times s. What is s? S represents the slant. So to show you where the slant is, here's the slant of a cone, and that is also present right here. And those represent those two represent the same units. And the height is gone when I unfold the cone. And the final formula, and we'll come back to this question, is the formula for a sphere. And the best way to get the sphere is actually to get a ball, peel off the paper or whatever the ball's made out of, and you'll see that it forms 4 circles with the same radius as the sphere. So it works out to 4 pi r squared. So we're going to go do now another problem using a cone. In this case, it was an EQAO multiple choice question, but we're going to take it a step further. It says find the radius, so we're going to do that, but we actually want to find the surface area of this cone. So that's what we ultimately want to do. Okay, so the first step is the only thing we are given here is the volume, and the volume is 1,000 centimeters cubed, which is the same thing as 1,000 milliliters, and that translates to 1 liter. So this fits about 2 bottles of water in it. So that's if you want to just think of how big that is. And we're given the height. The height in this case is 20. So we need to find the surface area. And that's the ultimate part of this question. We need to find the surface area of this cone. And you know the surface area of the cone is the area of the base, pi r squared, plus the area of the side, which is pi rs. So you can see, to find, we don't have enough information. We are missing the radius of the cone in order to solve this. So we don't have the radius. We are given, and take a look, we also need another thing for this. We need also the slant of the cone. So that's some information that is missing. So how can we get radius given the height and the volume? Well, now you have to go back to the volume formula. You know that volume of a cone is 1/3 the volume of a cylinder, which is 1/3 pi r squared height. Or you'll see it, my preference is seeing it like this, keeping it as a fraction, putting pi r squared height in the numerator, and then divide it by 3 in the denominator. So let's find the volume of this cone. Let's find the radius of this cone given the volume. So we're going to substitute 1,000 for the volume. We're going to use 3.144 pi. You know, I like substituting in brackets. We don't know radius, but we do know the height. And we divide by 3. So what do we do in terms of the steps procedure? So we're going to still follow the order of operations when solving. So I'm going to multiply, looking at the right side of the equation, I'm going to multiply 3.14 by 20. So let's do that. Get out our calculator. Let's move it in a place so we can see it. So we're going to use pi times 20. And I use the pi button. And I'm going to round to 2 decimal places. So 62.83. And at the same time, once I multiply, I'm actually going to divide by 3. So we're going to divide by 3. And I get 20.94. So just to recap, I multiplied this number with this number because this is all product. All 3 terms here are being multiplied. So I can multiply this with that. And then I'm going to divide by 3. So that's what I did to get my answer. So I get 1,000 equals 20.94. And I like keeping 2 decimal places. 20.94, and we're left with still r squared. So it's saying 20.94 times something gives me 1,000. So as you guys recall, I'm going to work backwards. Instead of multiplying, I'm going to divide both sides of the equation by 20.94. I can use trial and error, just keep on trying numbers that work to get 1,000. You can do that, but it takes a bit of time. It takes quite a bit of time. So a quick way is to just divide. So when we divide out, let's just get an accurate answer here. So I'm going to take 1,000, or fairly accurate, 1,000 divided by 20.94. And that's 47.75. So let's jot that down. 47.76, because I'm going to use 2 decimal places. 47.76 equals r squared. And as you guys recall, you're looking for 2 numbers that multiply to give you 47.76. The quick way of doing that is just using the square root button. And there we have it. The radius is 6.91. Okay, so now we have the radius. Actually, I'm going to put it down here so we can save some space because we're going to need that to find the surface area. There. So I'm going to erase that. All right. So now we have the radius, which is 6.91. So we can solve this part of the surface area. We can get the circle part, no problem. 3.14, we have the radius at 6.91. But the next thing, we're going to need a slant. We don't have the slant. All we have is a height and the radius. But I'm hoping you start realizing this is where you're using a tool within a tool, and that's perfectly normal. You can use tools within tools to solve your problems. So let's see if I can show this using a triangle. Try to make the triangle fit the model. There we go. All right, so now here's our triangle. And actually in the picture it showed it pretty well. I'm going to pull out this triangle to emphasize or to clean up what we see there. So this represents the slant of the cone, this represents the height of the cone, and this represents the radius of the cone, which is 6.91. And you know you're dealing with a right triangle. So you should be asking yourself, right triangles? Well, you know what? I'm likely to be, since I'm finding a side length, I'm likely going to use a Pythagorean theorem. So start labeling your triangle. Across from the hypotenuse, across from the right angle is a hypotenuse we call C. I like using the shortest side as A, so R is A, and B we'll call H. So we're going to find the slant. So we're going to write down the formula. A squared plus B squared equals C squared. And please don't write down the formula until your triangle has been labeled. So what is A? A is the radius, which is 6.91. We have to square it. What is B? B is the height, which is 20 squared. And we have to find C squared. So we're going to get out the calculator. And we're going to move it out of the way. So we're going to square this plus 20 squared, which is 400. 20 times 20 is 400. So we get 447.76. 447.76. And that is equal to C squared. So, you know, something times something's got to, it has to give me 447. 20 times 20 is going to be pretty close. It's 400. What's 21 times 21? Let's take a look. 21 times 21 is 400. And between the 441. So it's going to be bigger than 21, slightly bigger than 21. So we're going to put 447.76, and we take the square root of that, and then it's 21.16. So we take the square root, C equals square root of 447.76, and make sure you extend your square root sign across. C equals 21.16. And now we have all of the information for surface area. So we're going to calculate the surface area. So notice there's a couple of distinct sections of this problem. Our first section is labeling all, the formulas that we need, labeling the triangle. Second section is calculating the radius. So I should label that as find R. Third section is finding the slant. And now the fourth section is actually calculating the surface area of this. It could be a drinking box. A liter, that's pretty big. It's a bottle of water. So we're going to write down surface area. Surface area equals pi r squared plus pi rs. Let's do our substitutions. 3.14, radius is 6.91 squared plus 3.14 times radius, 6.91, times the slant, and the slant in this case is 21.16. Okay, so now we can, do order of operations, do the radius, do 6.91 squared first. So 6.91, we square it, times pi. And there's our first part of the equation. So 150 and now we're going to go I'll use pi. Pi times 6.91 times 21.16. It's lagging a little bit in time. So that's 459.3. 459.3. We're going to add the two together. And we get 609.3. And the unit, since we're dealing with area, is centimeters in this case, squared. Now, if you would like to actually visualize, so think about this cup can hold one bottle or two bottles of water. So if I were to create that with a piece of paper, how much paper would I need? Well, it's 609 centimeters squared. So I'm going to take the square root. What square paper would I need to create this this shape, to have enough paper to make this cone. So if I take the square root, basically my paper has to be 24 centimeters or 25 centimeters by 25 centimeters. So think about if you have a paper the size of a ruler, just a regular 30 centimeter ruler, a little bit smaller by a 37 ruler, that's how much paper would be required to create a cone that would hold 1 liter volume or 1,000 centimeters cubed. Okay, so now we're moving on to the final problem. This is for you to discuss and to try to solve. So this is like a consolidate, or prior to the consolidate. So if both cans share the same height, so we know both cans, so we're just going to list it. This is the beginning problem. This height and that height are the same. So the can, the prism and the cylinder have the same height, 12 centimeters. And that's approximately what the actual height is of a can of pop nowadays. Oops. And we know both have to hold, and this is the actual volume of a can of pop nowadays, 355 centimeters cubed, which is 355 milliliters. Well, it tells you pretty much, try to find the radius and the side length for the shape, but basically I want to see which one is cheapest to make. I wouldn't even ask this problem. So let's ignore that this question is there. Okay? So it says, well, which can is cheaper to make? So you're dealing with a packaging problem. So we have to find surface area. So I'm going to jot down the surface area of a can as 2 pi r squared. That looks a little messy. So let's do this again. 2 pi r squared plus 2 pi r h. And we know, so just to label, this is the h, and there's the r. And we know the surface area of this can is going to be 2 times the area of the base. So in this case, we're going to make it a square base. So it's 2 times the area of the base plus the perimeter, which represents the length of our rectangle, times the height. And here's height. So we need to, and just to make it where this is going to be a square-based prism, so in this case it's base times base. So if we can fix this formula up, surface area equals base squared plus perimeter times height. So we need to find this information. We have to find the surface area. The problem is we are given, so just to show you, we are given the height. Oh, I don't like that color. Of course, I always pick the best colors. I'm given the height for both shapes, and we're going to use the height in the formula. But notice we're not given the radius, which is here and here, and we're not given the side length, which is here, here, and here. So that's what we need to find for both shapes before we solve, okay? So how do we find the radius of the cylinder? Well, we just saw a question where we worked a little bit backwards, didn't we? So let me copy these two shapes onto another page. And we're going to add a blank page. Okay, ooh, we're dancing. Let's group it. That's okay, we'll lift it up. Okay, so now we know volume. Volume for a cylinder is pi r squared height. The volume of this prism is area of the base, which is base squared times height. So we know the volumes both is 355. Pi is 3.14. Radius we're not sure of, but we know the height is 12. So we do the same thing here. 355. Base we're not sure of, but we know the height is 12. So let's try to work this out. Get out our trusty calculator. I can trust it. All right. So we're going to work out 3.14 times 12. So I'm just going to use pi times 12, and that's going to give us 37.7. We're going to round, well, just to 2 decimal places, but there was a double 9 there. So 37.7 r squared. Then we're going to divide both sides by 37. So 355 divided by 37.7. I should have saved that in memory. Give me the answer previous. So now we get 9.42 is the radius squared. So we take the square root. And we'll get that answer there. So the radius here is 3.07 centimeters. Okay, so we're going to do now the same thing with this. But now I can just divide with the prism 355 by 12 and take the square root. So let's do that. 355 divided by 12. And I'm covering up everything. And we get 29.58 equals b squared. We take the square root of 29.58. That gives us b. So we get the side length of 5.44. Okay, so now I think we have enough information to go back and actually calculate the surface area. So all we're going to do is substitute this into the surface area formula. So let's punch it into the calculator. We'll do it all in one step. And you know what pi is, you know what r is, you know what h is. So I'm just going to do the calculation in one step. Pi times, oops, let me clear this. It's supposed to be, okay, so 2 times pi times the radius plus 2 times pi times the radius times the height. And we have the surface area of this can is 250.8. So surface area, 250.8 centimeters squared. We're going to do the same thing for this shape. We have the formula here. So the perimeter is going to be b plus b plus b plus b, or 4 times b. Okay, so just keep that in mind. So we're going to now start this. 2 times b squared 5.44 squared plus the perimeter, which is 4 times b, or it's 5.544 plus 5.44 plus 5.44 plus 5.44 times the height. Where's our height? The height is the same thing as 12. Equals, so we get 300 and look at the difference between the two cans. So if I find the difference, how much more does this can save? If I subtract 250 minus 320, there's a difference of 69.5 centimeters squared. So let's put that there. Difference of 69.5 centimeters squared on the can. Now think about that. How much is that? How much volume? How much surface area is that? That's just for one can. But let's say Pepsi Cola, let's say the daily, we have 30 million people in Canada, over 30 million people. And out of 30 million people, let's say each day there are 1 million cans of Coke or for Kepsi, I should say, consumed each day. So 1 million cans each day, and that's making it a little bit too much. Actually, we'll make it, let's say, 100,000 cans. 100,000 people each day in Canada drink Pepsi. So how much surface area would they save if they went to a cylinder? That's why, notice we're with a cylinder. I'm going to multiply that by 300,000. So we are saving, just by going with a cylinder, 6.9 million centimeters squared of aluminum switching to the cylinder can. And we can even calculate the cost of aluminum. How much does that weigh? That could be another project that we can start calculating. But notice the savings. This is why these Coke cans or these Pepsi cans are in fact cylinder, because it does also save much more money in the long run for designing or for surface area. Okay, have an exceptional day, and remember to get support when needed.